what I kind of want to start off with is where we're going with organic chemistry. This is one of the things that you are responsible for being able to do at the end of the semester, is given a starting material and a product, come up with some synthesis. What reagents can you use to react with that starting material to make what intermediate? What would you then do to, and not even that intermediate, that next product? Once you have that product, what can you react that with to make another product? Once you have that product, what can you react that one with to make another product? Okay, so what we're looking at here is a sequence of actual steps, reaction steps, not mechanism steps. That means each of those kind of middle grounds, we are looking at an actual neutral product that we would then go through and react with a new reagent to go through and make the next thing in the sequence. Okay. So this is where organic can be kind of fun. It's a lot kind of like the spectroscopy puzzle solving, but in my opinion, much, much more difficult. Right? Because by the end of second semester, you in theory know all possible reagents, and there's a lot of reagents. Okay? For each functional group, you're looking at a list of maybe 10 to 20 different reactions. By the end of second semester, you have 10 functional groups that you're supposed to know, which means you're looking at 100 to 200 different reaction conditions. Right? And within each of those 100 to 200 reagents, you can tweak the concentrations, you can tweak the strength of the base, strength of the nucleophile, to now generate something that is an entirely different product, but under the same general guidelines and circumstances. Okay? So try to not get too bogged down in just memorizing reagents. You will have to do that eventually, but you don't have to do that yet. Okay? What you should be focusing on is what things changed, and try and find where new bonds could form, where they potentially came from, so that you can work your way backwards, okay, or forwards. So if we're given this problem, we want to come up with all of those individual steps in between to go through this synthesis. Okay, so we've got two parts or two places in which we could start thinking about this problem. You can either start with the starting material, which is what most everybody does, and it usually doesn't work. Or we could start with the product, okay, and try and think about how we could work our way backwards. Okay, so think about it a little bit for a second here. Try and decide where you think you would go first. Okay, either the starting material or the product, and then think about what reagents you might use to either react with your starting material or react with something to make that product. So if we're going to start with the product, what we're looking for is a polar, and actually in both cases, we're looking for some kind of polar bond, some place where there's a weak bond that I could easily break or make in the reverse direction. Hi. A little bit of thought here, so maybe I'll pause it. Okay, so what you suggested was starting with the starting material, and you said we want to run some kind of radical reaction. Why do we know we need to run a radical reaction? It's non-reactive. Okay, we're starting with a starting material that has no reactivity associated with it. Your alkanes have virtually nothing. Okay? We're very limited in our abilities to react with our alkanes. To get them to react, we're going to have to do something kind of crazy. Maybe, perhaps something a little bit radical. Yes. Zing. I tell myself that every morning.
Self-affirmation.
So we're starting with an alkane as a starting material, which has very little reactivity, so we're going to have to use a radical reaction. Okay. With our radicals, what are we doing? What's the chemistry that you've seen so far with radicals? So initiators, we might see light, H nu sometimes, or heat. What else?
Chlorine
we're looking at doing something to get the alkane to react. So we're going to convert the alkane into an alkyl halide. Officially, it will go through a radical intermediate, but that's looking at the mechanism. I don't care about the mechanism. I just want to get to the next product. So our radical reactions will convert an alkane to an alkyl halide or halide. Okay? What halogens are there? Fluorine, chlorine, bromine, and iodine. Okay? That's an awful lot of choices to throw in here. Okay? So which one should we pick? We will always pick bromine. Why? It's what? It's selective. Okay? Meaning it's going to do the substitution reaction, a hydrogen for a bromine, in very particular fashion to generate the most stable intermediate, our radical intermediate, and that substitution is going to pick a hydrogen at our most substituted position, and we end up with that alkyl halide. If we use fluorine, what happens in the fluorine reaction? You probably won't have the opportunity to do another experiment. Okay? That's how violent it is. It's extremely violent, so we typically don't look at those types of reactions. Chlorine, also a little on the violent side, but it's not that bad, so we can at least control those conditions. The issue with chlorine, though, is because it reacts so quickly, it's not selective, meaning that chlorine will go anywhere it can. So it's going to substitute for any possible hydrogen. That then gives us a multitude of different products, and we're not going to be able to predict where we're going to go forward. Bromine kind of sits in a nice happy medium. It's fast enough that we can actually wait for it to react, but it's slow enough that it's selective. Iodine is ridiculously selective, but it's so slow that it just doesn't make any sense to run that reaction. Okay? So when you're looking at synthesis, bromine's our focus. Will you see questions on chlorine? Absolutely. Will you see questions on fluorine or iodine? Probably not, just because they're completely outside the realm of feasible reactions to run in the lab. Okay? So that did one thing for us. That advanced us one step forward. Okay? How much of that did we need to know? Well, hopefully you remembered the radical. Okay? And then so far when we talked about radicals, we only said you're using bromine. Okay? So you do need to know that reagent. If you didn't know that reagent, you could have gone based off of the type of reaction that we run with radicals, which is radical substitution. What atom is going to be easiest to substitute in a structure that is just carbons and hydrogens? Hydrogen, because it's on the outside of the structure. It's most readily available. Okay? That means we do that substitution, and then you could decide, oh, now we got a problem. Which hydrogen to substitute? Hope for the best. Pick the one that you want. Okay? So we've now fixed one of our reactions. So we ran a radical substitution reaction. Shouldn't write SN. Now where? Okay. If we did a regular substitution, where would our nucleophile go? Is that a valid reaction? It's a valid reaction, but does that get us closer to where we want to be with our product? No. Okay, what do we want to have happen at that position? Elimination. I want a double bond, so I need to do an elimination reaction. Okay, so I could go back and say, okay, well, the product that I want is putting a double bond there. Okay, well, what type of reaction did I have to do in that case? An elimination. Okay. So what reagents would I need to force the elimination reaction to occur? Okay. Heat is usually a big signal for it. Okay. We need some kind of base. Do we use a weak base or a strong base? Why use a strong base? Heat's going to help break that bond. I can still run an E1 elimination. Why use a strong base? If I use a weak base, I'm going to run an E1 elimination, which directly competes with SN1. If I want only the elimination to occur, better push conditions that are going to force the elimination. So I want to push which type of mechanism? An E2 elimination, which does not compete with the SN2. Okay? So I would want to use a strong base. Should I use the strong base that's listed, or let's put another one right above it? How about this as a strong base? The blue one is now a bulky base. It's still going to do an E2 elimination, but what's the problem? It's going to do the elimination in the least substituted position. Okay? So what you've got to do is stepwise through, pick something to work with. Once you've got that something, start to adjust it. Can we make a change to it? That blue version is so sterically hindered that we would get the elimination happening upwards. And that's not what we want in our final answer. So that doesn't make sense. Okay? Now what do we do? What was that? Substitution. To run a substitution reaction, what do we need? Let's just stick with the substitution for the moment. What do we need to run a standard substitution reaction? Need a nucleophile. What else? Leaving group. That's the one I wanted to zero in on, so let's stop with that. Do we have a leaving group in our structure right now? No. We need an alkyl halide. We need a halogen to act as our leaving group. I don't disagree with your substitution statement, though. And I'm not even going to push radicals at this point. You're still focusing left to right. What about right to left? What's the difference if we go backwards? We have that weird amine group. What bond would have to be formed? Try again. We're forming the sigma bond between the ring and that other group, which means if we split that open, what charge would I expect to happen on either side of that bond? Negative where? Both of them are carbons. The one that's specified is our C, and the other one should be positive. What kind of a species is negatively charged? Nucleophile. What did we just potentially find in the process of trying to look at the reverse? We found a reagent that we could go through and react in that last step. We could add, whoops, let me show the triple bond. This species, for it to react, it would need to react with, whoops, keep doing a rotation on it, sorry. Positive charge. Do we ever have a product that is positively charged? An intermediate would be positively charged. I'm not asking for intermediate. This has to be a product. What does that nucleophile need to do? It needs to attack the positive. How did that carbon become positive? It lost something. That something would be? Fair enough. It lost electrons. You're absolutely right. Okay. Would it be a hydrogen? So what we're suggesting, if we put on a hydrogen here, would we expect the hydrogen to take the electrons away? No. So what atom would be a good thing to put there to take electrons away from that carbon? How about a halogen? Okay. And we could have any pick we wanted of any halogen we want. Okay. You'll notice that I'll keep falling back to bromine. Any ideas why bromine? It's a really good leaving group, and I have a nice selective way of putting bromines onto a structure via free radical reactions. Okay? So what we did is took one step backwards. Okay? Personally, I probably would have done that first, probably would have done the radical to begin with, and then the one step backwards on the far right. Okay? And then tried to evaluate what potentially occurred. How many steps are we missing? Just one. What needs to show up? What reagent has to be there? Minimally, it has to supply bromine. Has to. No choice. Okay. What else is going to go with that bromine? If I wanted that bromine to come in, okay, and react, where do I want it to react in that starting material that I've got? Okay, that blue carbon. What chemistry is located at that blue carbon? It's an sp3, bunch of hydrogens attached to it. Is there really any chemistry associated with that? No. What functional group am I looking at? An alkane. How do I get alkanes to react? I need heat or light and a radical reaction. So I can now tag in my heat or light to say I'm running a radical. What reagent supplies my radical?
Peroxide.
Peroxide is going to supply a radical that would then react at that position. What we're trying to do is still focus on getting that bromine to react to that position. So peroxide is a good initiator. We don't need to have that there. We could put in Br2. We seen that before, like in our very first step? Yeah. There's an added wrinkle that we haven't talked about so far this semester because we haven't evaluated alkene chemistry yet. But that pi bond can potentially react as a nucleophile. Okay. Given the right conditions, a high enough concentration of bromine, and what we end up getting is the addition reaction instead of the free radical substitution. If we want to limit the addition reaction, that means we want to limit the concentration of Br2. And what we can use instead is the reagent NBS, or N-bromosuccinimide. Okay. Why did we not use NBS to start with? We didn't have the pi bond to worry about a concentration issue. So we said, who cares? Let's just use bromine. Could we have used NBS then? Yeah. NBS still is going to supply bromine. It's just going to supply it in a much smaller concentration. Why would that be nice? For those of you in lab, remember that comment that my postdoc made about bromine?
Oh, very bad.
He was afraid that it made him sterile because he worked with it for so long. So which would you rather work with, a small concentration of bromine or a high concentration of bromine? Probably makes sense to work with the smaller, I guess it depends what you're trying to do. You usually are going to work with the smaller concentration of bromine, so you would typically go through and use NBS in all circumstances. Okay? Kind of makes sense on how you go through and approach these types of problems. Okay. The alkanes should be a giant red flag. The first thing you got to do is radical. So radical it up, get some kind of product, and then start to deal with what you've got. Okay. The rest of it is trying to find a balance between what chemistry you have, identifying bonds that can be broken, bonds that can be made, and just kind of working your way slowly through it. What if you'd started making the wrong bond? What if instead of trying to make the pi bond first, we tried to make that last bond first? What would the result be? It's unfortunate. Probably wouldn't work. So what does that mean? Spend 5 minutes doing something that didn't work. Oh well. Worry about it later, go back, try again. Okay. When can you get to the point where you're really fast and you're always right on the first try? Practice. Lots and lots and lots and lots of practice. Yes?
If we're going to see something like this on a test, would we expect it to show every mechanism? Like with arrow
No.
marking?
What I would expect, so this is exactly how I might phrase it on a test, is just get me from point A to point B. I don't care how you do it, just do it. Okay? And what I'll supply would be intermediate steps. I think you can do this one in 4 steps. If you can do it in 5, by all means, do it in 5. Okay? If you can do it in 3, nice. Way to show me up. Okay? They have to be 3 valid steps, but okay. So in the process of going through these, draw each of those structures. So it's one of the things that's kind of frustrating, in my opinion, with sapling, is that when I watch people do that homework, what do you end up doing? You draw structures on sapling. Cool, you're getting the practice on drawing on a computer. Where's your test? On paper. You should not be doing the homework on the computer screen. You should be drawing it by hand first, then taking your drawn out answer and putting it into the computer. Otherwise, you're defeating the point of the homework. Okay? Questions about that? Already behind schedule. I said it was going to be done in 30 minutes. So, our reaction summary. I did kind of cut some of the reactions out of this. We've got our alkanes. As far as the reactions, we've got bromine and light. We could also throw in NBS there. Should have included that. Still requires light to initiate or heat. And then you could also do chlorine. So this little reaction summary is kind of nice because if you're given that starting material, which one would you use? Bromine, why? You get 1 product as opposed to, I don't even know how many I listed, 4 products. Okay? So in each of these, what I would refer to as spider diagrams, I'm trying to include some of that secondary information about deciding which reagents to go through and use and what things you might see. Yes?
Why is it that chlorine makes that many products?
It's because the chlorine is not selective. So in the very first or second step of your alkane or your free radical reaction, that chlorine radical is going to react with the first available thing it sees. That first available thing will be hydrogen, and it will generate whatever radical comes out of that because the chlorine radical is so energetically high that it doesn't matter how stable the alkane radical is, it's lower in energy than our chlorine radical.
So it's a better base. Not necessarily.
Why avoid the base statement?
Because then you're talking about elimination.
No. If I was going to look at chlorine as a radical, how would I draw it?
Oh, just with 1 electron.
Right, with 1 unpaired electron. If I was going to look at chlorine as a base, how would I draw it? The negatively charged, it has all those paired electrons. Those are drastically different structures. Okay, drastically different chemistry associated with it. Okay?
We are more selective just because it's bigger.
Yes. It's bigger, so what the bromine can do is stabilize that radical, that unpaired electron, better. Okay? The other functional groups we've got are alkyl halides. This is misleadingly simple, in my opinion, with the alkyl halides, because you'll notice that there's very little specifics as far as the strength of the base. Oh, I guess I could have added that one on there. I did at least a reasonable job with the substitutions. If a weak nucleophile, we're pushing the SN1. Strong nucleophile, we're pushing the SN2. And you're seeing different results coming out of it. You'll notice that in the SN1, I provide both the retention of stereochemistry and the inversion of stereochemistry because we potentially get both. Why would we get both? Because we have a carbocation. You'll also notice that I provided a third product where the nucleophile is at a different carbon. Why? Because with a carbocation, we need to evaluate for rearrangement. So I picked a starting material that would allow for a rearrangement. Will you always see a rearrangement? Nope. The only time you see a rearrangement is if you actually make something more stable. If it's not more stable, it doesn't go forwards. And you'll stick with that the carbocation that you started with. With the SN2, I drew it immediately as the inversion of stereochemistry, and we end up with that one product. Why do we not see a rearrangement? There's no carbocation to rearrange. With a base, we run the elimination reaction. With that elimination, there's all sorts of things that are dependent on that. Typically, you'll end up with the same product, E1 or E2. Why? They're both making an alkene and their alkene product. The one that's favored is the most substituted alkene, which means both E1 and E2 are probably going to get you the same product. So how would you know which mechanism occurred? Look at the strength of the base. Okay. The very last functional group is the alkenes, which we've really only seen one reaction, sort of, and that's looking at our NBS. So we're doing a free radical substitution reaction again with our alkenes. You'll notice that I've drawn two products. Why did I draw two products?
That one is a allylic, so it's also kind of stable.
The most reactive position in that alkene ends up being a primary hydrogen on the end, but it is primary allylic, which means one of our intermediates will be the radical. Draw that to the left. That's my right. Our radical out there. Primary radicals, are those particularly stable? Nope. So what happens? What's the relationship between these two structures? Not structural.
Constitutional.
Not constitutional. Not stereo.
Resonance.
It's resonance. They're one and the same. Okay, between these two, which is the most reactive part of them? The radical is the most reactive part. Okay, which means if we're looking at an intermediate, we want to form the most stable intermediate, which is going to be which one, left or right? The right, which means when we look to our products, we're going to put the bromine reacting with our far right structure, which gives us the major product shown. Okay? This is kind of a weird one to put under the alkenes because it's still an alkane that is technically reacting. But that pi bond, oh, that's not a good sign. That pi bond, if that's popping up, that means I've lost connection. That pi bond is contributing to stability within the overall structures.